Hello folks, this is tutorial number 13 in a playlist on meshing of the finite element embedded within 3D Experience platform. Now keep in mind that the finite element embedded there is actually the Abacus program. In this tutorial, I would like to discuss the concept of shell offset, how it's used and what it's good for in the context of an example that we will see. However, as usual, I start with some explanation of what's going on. So, generally speaking, shells go on surfaces, and in many cases, the surfaces that are provided to you or you created are the middle surfaces. Although, in the case where, for example, laser scanning is done to find the coordinates of a particular part, that surface is usually, well, I mean, it's the top surface, whatever you can see. But in many cases, that reference surface where the mesh is placed on is the middle surface. So here's a surface. Suppose we take a shell, four-noded shell like that, and let's say that the middle plane of that shell is what is shown in the dashed, for example, dashed line. And what we do, there is a half of the thickness on top, half of the thickness below it. But generally speaking, we don't draw those top and bottom surfaces. We draw it like that. But we understand that in this particular situation, this dashed four-noded element is on that surface, which is the middle plane. Now, let's look at some examples. I'm going to look at the view from the side so that it's an extruded surface. I don't have to look at the three-dimensional effect. Suppose this is a surface, but which is going into the screen or coming out of the screen, either way. So when we model it with the shell element, essentially we say that, okay, approximate the surface, approximate that curve with the plane, which you can see there. That is the middle plane. Half of it goes up, half of it goes down. So this makes sense if the surface that's given to you is the middle surface. And in that case, you don't have to do anything special. There is no offset. Offset is none. Well, what if you're told that this actually is the bottom surface? In other words, the shape that's given to you, the surface that's given to you is the bottom surface of whatever you're trying to model. So that being the case, it means that this is the setup. In other words, the middle of the shell, which is that dashed line, is not actually sitting on the surface. It's half the thickness above it. So this is a situation where the offset, you have to specify it, as you will see, as the bottom surface. You have to indicate that the surface that you pick is the bottom surface, okay? And here's the other situation. Suppose that the surface that's given to you is actually the top surface, and you want to model that. So that means that that shell element that you draw and its middle surface, middle of the shell, that dashed line is not actually uh, is uh, is not actually on that surface above it, but this is the case where we have the top surface, and as the offset, you define it to be the top surface. You'll see how that is done. Just keep in mind what this thing means is that the surface that's given to you, the coordinates of the shell elements must be internally adjusted. In the bottom two cases, it must be physically internally adjusted for computational purposes. Now, you're not going to see that, but it is adjusted depending on whether you say it's the bottom surface or the top surface, and it's not adjusted if you say that it's the middle surface. So here is the shell section dialog box that you get in 3D Experience. Notice at the very bottom, under the advanced, at the very bottom, offset definition, there is none, which means that already if the surface is the middle surface, don't worry about it, none. But if your surface that's given to you is the top surface or the bottom surface of the object that you're trying to model, then you have to specify the offset definition depending on what it is to be top or the bottom. Okay, so this is none if whatever you're doing, that surface is already middle surface. If the surface that's given to you is the top surface of the object that you're trying to model, then you have to define the offset definition as the top surface, and finally the bottom surface. When we do things like this, internally the coordinates of the shell are changed to position in the right spot, as I mentioned to you. But we're not going to see that, okay? But it's internally done. Let's do an example of a very simple plate, okay, which we're going to model with shell element, as you see here. One end of it is clamp, and the other end of it is pushed down through a punch. Now, you might say, wait a minute, if there was no punch and I had a plate clamped at one end and I wanted to apply some kind of pressure on it, it really doesn't matter whether it is the top surface or the bottom surface or the middle surface. It makes no difference. But when the problem becomes more complicated, when there's interaction is involved, then of course it matters whether you're dealing with the top or the bottom or the middle. So that's what we're doing. We have a contact problem here. So instead of doing a very simple problem and showing it to you in the context of a cantilever beam that's pressured, or a cantilever surface that's pressured, I'm going to do this problem. Okay, so we have a punch up there with these dimensions, and it's going to move down, and at some point it's going to touch this shell. It could be the top one, it could be the bottom one, it could be the middle one, depending on how you look at it, and you want to model this. This is not drawn to scale. All dimensions are in the millimeters. By the way, I should eat my words. That punch does not touch the bottom surface, so you know that. Okay, so here's the situation, and I have modeled this thing in 3D Experience, and I'll do it with you. So these are the two parts. Of course, the punch I'm going to model as an analytical rigid surface. We just use it, you do it like that. And here is the way it's meshed. Okay. And just keep in mind, because we're doing it as two parts, you have to make sure that both the two parts, namely the die and the analytical rigid surface, are included in the finite element model. We'll see that. And if things don't work out, the first thing that you should do, depending on the error message that you get, you come back and flip this direction. Okay? We'll get there. I'm going to assume that this is done with general contact, so that I don't have to worry about the primary surface as the secondary surface and the green and magenta, with the surface to surface contact. I'm going to do it as general contact and no friction. Okay. Okay, because I'm dealing with a problem that involves two parts, namely the die and the analytical rigid surface, I need to start with an assembly design. So let me go ahead here and start with the assembly design application and immediately insert my first part. So insert 3D part. And I'm going to call this thing the die. So properties. So die. All right. And we're going to make it. And to make it, I'll go double click on the 3D shape. And on that vertical plane, sketch. A line. Notice that it is snapping to the grid point. There's nothing wrong with it. It's just that if you don't want it to snap to the grid point, what you do is you go to the uh, uh, constraints. Sorry, let me see now. You go to the dimensional constraint and say don't snap to the grid point. It's entirely up to you, but yeah, let me uncheck that so that I can just draw it anywhere I want. All right, so let me dimension this thing to be 40 millimeters. But I want it to be symmetric with respect to this. So there are different ways of doing this thing. One is to put a dimension from here to there, for example, or you can select this, control that, and dimension, right click, allow symmetry line. So there we are. It's entirely up to you. So exit. We're done here. So we're going to exit. and extrude this thing by 120 millimeter on the surface. Extrude 120 millimeters in the direction that is shown, in the direction Y. Okay, so let me apply a proper material property on this thing, because the other one is analytical rigid surface. It does not have any material associated with it. So, but here I'm going to go tools, create a material. I will call it dye um, January 7, 2024. Say okay. Once it appears in my table over here on the right hand side, I'm going to apply it and then apply it to the part. The numbers, of course, we're going to put down in a minute. Okay, let me refresh this thing, maybe it'll be faster. Oh, okay, we'll try it again. Create a material, dye, January 7, 2024. You say okay. There we are. Oh, this is the one that got timed out. This is the one that I just did. Okay, it doesn't matter. So I'll apply this one and close that on this part. And we're going to put in the numbers. And all it is actually steel property, elastic steel properties. So under structures, abacus multiphysics, mechanical, elasticity, and put down 200 gigapascal, 200 GPa, Poisson ratio 0.3, and say okay. Pretty much done. Okay, so let's go ahead and insert our next part, which is the analytical surface. So I'm going to go there. I'm going to go all the way to assembly. You can see that assembly design. Right click, insert, another 3D part. I'm going to call this thing ARS, analytical surface. Right click, properties, call ARS. Okay, and we make it. Double click on the shape on that vertical plane, on this same on this vertical plane. Yeah, on this one. I'm going to sketch half a circle. Notice that I did uncheck the snap to the grid point, so I'm going to have to fix this thing in a minute. So the radius of this thing is actually 20 millimeters. All right. And the distance from that point to this is the center, the distance from the center of the circle to the middle surface, which is right here, is 30. So let's go back there. So the dimension from this point to that line is 30. What happened here? From this point to that line, that dimension is 30. Okay, good. And exit. Now this I'm going to extrude in each direction by 25 millimeters. So we go to surface, under extrude. Here's the symmetry. See that? See this icon? Symmetric. 25 in each direction. It means gives you a total width of 50. There we are. And incidentally, I can hide this sketch. So there is our geometry. I do need a reference point here. Now the reference point, you can use any of these corner point or anywhere you want, but I will actually literally make a point. So let me make it. While I'm in this part, I'm going to say create a point. And okay, so let's see now, maybe 100 up. See, yeah, right there. See that 100 from the XY plane, global XY plane is going to be right there. So we have a reference point up here that I'm going to be using later on for movement of the sky. Save everything. We don't need material properties, so go all the way to the top, and we're going to go, see, I'm at the assembly level. Just make sure you're at the assembly level because I want to create my elements at the assembly level. So right click, where is that? Structural scenario creation, and just wait, select your model, select your, oh, I'm sorry, I should have gone, not, that's the wrong spot. Okay, what I meant to say was to go to the meshing structural model creation. We haven't meshed it yet. Okay, good. Empty FEM model, and just make sure that you select both of these, okay, because these are both going to participate. And notice that because of the way I did it, I went all the way to the top at the assembly level. The finite element model is created at the assembly level, which is fine. Now, let's mesh the sky. So we're going to go to measure, uh, surface quad mesh. We're going to mesh the die 5 mm. So we're going to get a mesh like that. We don't need to mesh the analytical ridge surface, so we just leave it the way it is. That's pretty much it. As far as the finite element, properties. Let's do the properties of this shell. Otherwise, because you have to come back. If we don't do it now, we have to come back. Properties. Let's see now. Under properties, shell section. Select that surface, and this is where it's important. Notice that the thickness of the shell is 10. You know that. We are assuming that this is the middle surface. That's our first run. So, and notice that because of that, I don't have to do anything. No offset is necessary to specify, because if this is to be the middle surface, then we don't need to specify where it is. Good. So let's quickly save this. And now we're going to go to scenario creation. So structural scenario creation. Last time when I went there, there was no finite element model. I knew that I forgot something, and that was create the actual finite element model. So we select it. It's a structural problem. Okay, so let's do a few things. First of all, this end is clamped, so we're going to go to boundary condition. Clamp, you can either use the clamp icon, or you can, if you want, use the. Oh, before I do that, notice that these are all dimmed. That's because I haven't specified my procedure yet. So click on the procedure. We're going to do a static one. And notice that by default, the nonlinear geometric effect is included, which is fine. And now when I go to boundary condition, I can actually select stuff. Before I couldn't do it because there was no procedure specified. So let's go to the, you can use a clamp, or you can use the fixed displacement. I will use fixed displacement. So all 6 degrees of freedom are fixed. And then this surface is can move only up and down. So another fixed displacement on this surface, which incidentally, uh, maybe, oh, you know what I forgot to do? I forgot to create the analytical rigid surface. No problem. Just leave this the way you are. Go back to finite element model. I just forgot to do the analytical rigid surface. As simple as that. So under abstraction tab, under the abstraction tab, find the thing that says analytical rigid surface. It may be hiding in this whole thing. I mean, for example, yeah, maybe this may be on the top, this may be on the top, but expand it so that you get the analytical rigid surface. Select that, and for the reference point, select this. I'm sorry, I forgot to do that. Now we're doing it. Now, this is the flip direction that I was talking about. Let's leave it the way it is, and we see that if there is a need to come back and reverse this. Okay, now we're going to go back to our scenario. Remember, I did go to scenario. I realized that I forgot to define my analytical surface. And let's go ahead and find out. See, this was missing. This was missing before. Okay, so we go to a boundary condition, and let's find out fixed displacement and select this. Notice that the analytical rigid surface is selected. Before, when I forgot to actually create the analytical rigid surface, when I selected this, it says face. I knew that there was something missing. That's why I had to go back. So this thing can move in the direction Z, but cannot move in direction X and Y, and obviously cannot rotate either. So we say, okay. And now we apply a translation. Right here, where you had the fixed displacement, apply a translation. Once again, if you select the surface, it's going to put it on that reference point. I can select the point here, I can select the reference, the surface, analytical rigid surface. Okay, so here's the situation. We're going to make this thing move by 5.1 millimeter down. When that happens, it's going to touch the top and it's going to push it down, okay? So we put down negative 5.1 and we say, okay, all right. Let's define the contact interaction between them, because if I don't do that, this is going to go down. It will never see this fellow at the bottom. So under interaction, I do general contact. Scroll to find the general contact. You don't have to do surface to surface and select the primary and secondary surfaces, etc. When you do general contact, it's going to do it for you. And because I'm not specifying any friction coefficient, it assumes that it is frictionless. Otherwise, you have to define the, what is that? You have to define the contact property, which I don't want to do. It's frictionless. Good. So save it, and now we're going to run it. Hopefully, it's going to touch this thing and push it down. Hopefully, we'll see. So under the simulate, let's just quickly do a model and scenario check to pick up any obvious mistakes. Let's do the simulation check once again to see if there are any obvious errors. Remember, 5.1 down should touch the top surface and should push the plate down. It should. If it doesn't, there's something wrong. Of course, we're going to have to fix it. So now we're going to run it. Excuse me. Well, it didn't push it down. Okay, didn't push it down, so there must be something wrong. And this is where I suggest my first reaction is go and flip these directions. That would be my first thing that I'm going to do, because it looks like it didn't see that guy. It didn't see the top surface of the shell element. So what I'm going to do is I'm going to go to the analytical rigid surface right here, double click on it, and flip this. You won't feel anything, and go back to scenario and run it again. And if it doesn't push it, means something else is wrong, which we have to fix. But let's see. 5.1 should have touched. Motion of the punch by 5.1 should have pushed that beam down, developed some stresses in it, basically. It didn't do it in the first run, so I went and flipped the surface, and I'm hoping that will take care of it. And we say, okay, there we are. Now, to convince you that is in fact the case, if I go and push this thing down by 5 millimeter instead of 5.1, then again, there should not be any stresses. Let's check it out. We go here to boundary condition, push this thing down by 5. We say okay, and go back to scenario. We are in a scenario, so we're just going to go run it right there, simulated. So it should reach that top surface and stay put there. No stresses develop. No stresses. One thing I want to show you, let me left double click on this and select the last tab and say, show me the shell thickness. You see? You see? It reached that and stopped it. Now, one other thing, say okay. If I say right click visibility manager and I say, okay, also show me the part. There you are. You see? The middle surface is here. That's the surface that we created. It's right there. Okay? Think about it in that sense. And anyway, let's uncheck that. I don't want to see any of these. Let's go back and let's go and this time say that this surface that we meshed it is actually the top surface. Okay? The top surface. So we go all the way back to properties. Properties. Okay. Under advanced, we say that this is the top surface. So top surface. So let's see what does that mean. If this is the top surface, that means we have to push this thing by 10 millimeter and still nothing happens. Let's check it out. But if we do a 10.1, it's going to push it down. You say, okay, top surface. And I'm going to go back to scenario. Okay. And that displacement, I'll make it 10.1. How about that? 10.1. So let's go here. Let's go and make this thing, first of all, let me make it 10 to convince you that nothing will happen. Where is that translation? 10 minus 10. And there should not be any stresses developed in it. Let's go ahead and run it. There shouldn't be any stresses. But if we do 10.1, there will be stresses in it. So you can see why that thing's so important, because the contact requires to know where this shell element is, the top and the bottom surfaces of it are. Should have zero, should have no stresses. There we are. But if we go back here, make it 10.1, minus 10.1, you will see that there will be stresses. So let's go run it. 10.1 should give you Negative 10.1 will give you stresses. Because it's pushing it. There we are. One last thing. Let's go and make this thing the bottom surface. Let's go make this thing bottom surface. We go back here. We go back to the shell section. Make this thing the bottom surface. And notice that because we made this thing the bottom surface, even if we applied 0.1 displacement of the punch, it will push this thing down. So let's go here to the apply translation. Even a 0.1, negative 0.1 will push this thing down. Okay, and run it. It'll push it down. Because to say that that is the bottom surface, uh, that means the top surface is created by going 10 millimeter up. As soon as you go 10 millimeter up, it touches the punch, and as soon as the punch starts moving, the contact is already there. So a motion 0.1 millimeter will develop stresses in the beam right there. And once again, if you don't want to see this thickness effect, double click on this. Don't show me the thickness effect. If you feel more comfortable, there we are. All right, so that takes care of this tutorial, and I hope you found it useful.